Okay, thank you very much for the introduction. And in a way, I'm quite pleased by the audience in front of me because it means there's no number theorists to be bored by the things I'm going to be describing. So, as the title suggests, I'm going to be talking about supervised learning, which is a paradigm in machine learning, perhaps the easiest one to understand, and some arithmetic invariants. And those ones include class numbers, ranks of elliptic curves, and other things attached to number fields and elliptic curves. So they're all numerical invariants, which we're going to treat as labels to the data and see if a machine can learn them. So here's an overview of today's talk. So we're going to begin with some motivational context. So what that really means is a set of open conjectures, why you might want to take a different perspective on these things. That some of them are quite old problems, 200 years old, that nobody's had any serious insight into for a while. So yeah, I regard this as motivation for studying it this way. Then I'm going to give a bit of an overview of the supervised learning methodology. So it's not an extensive introduction to how to do that, but I'll just give you some experimental steps. And then there's 3 case studies, different things of interest in number theory, number fields, kind of the backbone of number theory, hyperelliptic curves, which are algebraic curves defined over number fields, and random matrix training, which we'll get to in the end. And then finally, I'll conclude with a page of adverts. Since this is an online talk and it's going on YouTube, I feel it's appropriate for me to afford some advertising space. Okay, motivational context. So just to recap, I'm going to go over some open questions, some of which are very famous in this first section. So you probably remember that number fields are defined by polynomials over the integers. So I've written down the examples of polynomials of the first few even degrees, and these examples are chosen to be extremal rank. So the ring of integers in a number field is a finitely generated abelian group, and the rank there refers to the rank of that group. So we have x squared plus or minus 2. They're both defined degree 2 extensions, and the first one defines a real extension. It can be embedded into the real numbers, and the second one is an imaginary extension. So these are called the real case, the real quadratic case, and the imaginary quadratic case. And that is quite easy, but I write down that terminology there just because there will be a focus on real quadratic fields. There are many interesting questions about them. And then there's a couple of degree 4 polynomials, and they're chosen so they're irreducible polynomials, I should say, and they're chosen so as to be totally real and totally imaginary, meaning in the first case all the roots are real, and in the second case all the roots are imaginary, and correspondingly they have maximal and minimal rank for degree 4, and then some degree 6 polynomials, and the same comments apply, only now the relevant ranks of 5 and 2. But the first one has all real roots, the second one has all imaginary roots. And there is an invariant of a number field called the signature, which is a pair of numbers, R1, R2. And R1 is the number of real roots, and R2 is the number of conjugate pairs of complex roots. And using these numbers, you can write a formula for the degree. So that's R1 plus 2 R2. Obviously, that's the number of roots of the polynomial. And the rank, this is Dirichlet's unit theorem. It's R1 plus R2 minus 1. So one of the things we'll try and learn is this invariant, the signature, which should encode these degrees and rank invariants. So I realise I've said things like ring of integers there. Is everybody clear with what I mean by that? Okay, it seems to be. Right, so like I said, there's going to be a focus on real quadratic fields in this talk, so we can be very concrete about that. So for a square free number d, no prime factor divides it to order more than 1. Q root d is just the vector space spanned by root d over q, a plus b root d for a and b in q. And a famous story in the history of number field is that unique factorization fails as soon as you pass from the integers to bigger rings. And the first example you might see is q root 10. So the number 9 is obviously 3 times 3, that's one prime factorization, but it's also 7 minus 2 root 10 plus, multiplied by 7 plus 2 root 10. And the key point there is if you calculate the norm of 7 plus or minus 2 root 10, you get 3, actually. So these two numbers on the right-hand side, they're also prime in this bigger ring. And the way you can see that is through calculating the norm. The norm's multiplicative. So to quantify this failure of unique factorization in any number field, there's a notion called the class number. And it's a number, I'm not going to define it, but if it's 1, the ring of integers has unique factorization, and if it's anything bigger, that fails. And I mean, you can think of it homologically. It is an obstruction. I know your geometers here, so you might like to think of obstructions, and you can put it in an exact sequence like that. But it's just a number, and for our purposes, if it's 1, it's got unique factorization, and if it's not 1, something else happens. So here are a few examples of class numbers of real quadratic fields, and what I've done here is for each small class number, I've written the first few examples of each, and then I've written a couple of big ones just to show that they persist beyond small cases. So for class number 1, the first few square free numbers are all unique factorization domains, 2, 3, 5, 6, 7. And the first one that's missing is 10. So 10 is 2 times 5, it's square free. And that was the example in the previous slide where we show unique factorization fails. Then I've written one that I think might be 2,029,000. Let me just count the number of zeros. So you still get class number 1 even for very big numbers. Class number 2, the first few examples are 10. We've already seen that one, 15, 65, 85. And then I've written one in the 5,000s. And then the same for 3 and 4. You can look at the numbers in your own time. And then I've also given an example of quite a big class number 21. I've given a few examples of when that occurs. So I should say I've got all of this information from the LMFDB. I haven't calculated all of this. There's a huge database of these things online, which is actually very important for this project. We need a lot of data to do this kind of experimentation. So a problem, like I said, it's a famous problem and it's a known problem. The Gauss class number problem from 1801 is, does Q root D have class number 1 for infinitely many square free D? And as you can see, it does indeed have class number 1 for some very big D, but you can't really get much further than that computation. So one of the motivational questions was if we could see whether any machine learning techniques would give a heuristic or an insight into this. For example, if we were able to interpret a successful prediction of class number 1, or if there were some generative methods that maybe gave some examples. So yeah, I guess we're looking at machine learning to give us some heuristic, although we're not there yet. So now the second main object in this talk, elliptic curves. So a couple of famous theorems. The rational points on an elliptic curve defined over Q form a finitely generated abelian group. That was proved by Mordell in 1922. A more general version of that is called the Mordell-Weil theorem, which applies to abelian varieties over more general number fields, but we'll only ever be thinking about elliptic curves over Q. And so it's got a rank part and a torsion part, and a theorem proved in, I should have checked this, in 1977 or 78, is that there are 15 possibilities for the torsion subgroup, and you can make them explicit. I just don't have enough room on the slide to explain that. So as for the rank, there are elliptic curves of the first few ranks, and here's a few examples with rank 0, 1, and 2. So rank 0, we have y squared plus y is x cubed minus, that should be x squared, sorry for the typo. Rank 2, we've got y squared plus y is equal to x cubed minus x. And rank 2, we've got y squared plus y is x cubed plus x squared minus 2x. So all those polynomials and 2 variables that define affine elliptic curves. And conjecturally, asymptotically, 50% of all elliptic curves over Q of rank 0, 50% of rank 1, and 0% have any other higher rank. So there is actually a record for the largest rank known, and I think it's 27, and it was sometime in the 2010s that was proved. And I haven't written it down here because the coefficients are, 19 digits long or something. They're very big numbers involved. So a famous question, not dissimilar to the class number problem, is which integers R can occur as the rank of an elliptic curve over Q, or is a set of R bounded? And I read in this paper I was just telling you about the rank, the record rank of an elliptic curve, that this question actually goes back to Poincaré, 1901. Which is curiously 26 years before it was proved that it was a finitely generated abelian group. So Poincaré had some insight there. And another very famous conjecture, obviously, about the ranks is the Birchon-Swinnerton-Dyer conjecture, which emerged in the 60s through computational means. And it says that the rank of an elliptic curve is equal to the order of vanishing of the elliptic L function at s equals 1. So I will define what that elliptic L function is later. And actually, less relevant to this talk, but I should clarify that there's a formula even for the leading Taylor coefficient involving certain invariants. So there's 2 big famous questions about ranks of elliptic curves. And again, the motivations are the same, whether we can, especially the first one, whether any generative techniques or any machine learning techniques give an insight into that. And the second one, I think, is just an indication that the rank is indeed very interesting in modern number theory. So I'm about to move on to the second section, so maybe this is a good time to solicit questions about the motivation here or any of the objects I've mentioned. Okay, I'll just check my notes. Okay, so we'll move on to the second section. So this is supervised learning methodology. So like I mentioned right at the start, supervised learning is a paradigm in machine learning more generally, and it's what you do is you give a machine a lot of example problems complete with solutions, and then you ask it to solve similar problems without showing it the solutions. So it's supervising that we know some of the answers. So here's a more detailed description of what I've just said. So given a set of vectors u and a label for each, so for each u and u a label lu, consider the label data set, which we call D, which is just the set u goes to lu as u ranges over capital U. And we choose a subset T, which we call the training data set, and its complement V, the validation data set. And we train the classifier on the set T with the standard supervised learning algorithms. So you might know some of them, the random forest, logistic regression, naive Bayes will all appear today. And for each u in the validation set, we ask the classifier to determine its label, and we record how accurate and how confidently it does that. And then because there is a bit of ambiguity in this subset T, so what we tend to do is we randomly sample it and we repeat it for lots of different randomly sampled T. We try to avoid picking special T that might give away the whole game. So a naive implementation of this would be to note that both number fields and elliptic curves are defined by polynomials. And obviously we can take the vector where those polynomials, the coefficients of those polynomials are the entries in the vector. So for a number field, we have the defining polynomial, like we saw on the first slide, and for elliptic curves, we have the Weierstrass equation, examples of which were given in that table of ranks. And we can ask a classifier trained on these polynomial coefficients to predict, for example, the class number or the rank. And the experimental outcome obviously depends on the specifics, but typically it's no better than guesswork doing this. And you know, one obvious reason for that, for example, if you've got a quadratic field, there's typically only one non-trivial coefficient. So it's like trying to get it to predict a number based on one other number. It's no better than guesswork. So the basic objective on today's talk is to find better training vectors.
Can I maybe quickly chip in?
Yes.
So I just was a bit confused how you did the previous slide. So you really take a subset of the labels, or you take a subset of your training set?
Yeah, you know, I noticed this when I was reading my slides. So the point is, you take a subset where you tell the computer the labels, and you take a subset where you don't. And the way I've presented that on the, you're asking kind of a pedagogical question how I've presented that on the slide. And I noticed this ambiguity myself, but I didn't have time to correct it. So the point is, T is the one where you show the computer the answer to the problems, and V is the one where you don't.
Okay, thanks.
And I accept that that slide should probably be rewritten. I was hoping that no one would spot this. Yeah, okay, so here's how we're going to define the better training vectors. So what we're going to do is we're going to use the L functions. So L functions are absolutely ubiquitous in number theory. And for example, you can attach them to number fields, you can attach them to elliptic curves. So a generic L function is a Dirichlet series, and that is of this form: an to the minus s as n goes over the positive integers. And the an don't grow too much, so it converges for a real part of s large enough. And in this talk, although it's not true in absolute generality, but in this talk, these an will be integers. So the training vectors we're going to take are just going to be some truncation of this Dirichlet series. So we take a positive integer m, and we define the vector, the first m Dirichlet coefficients of the L function. And L functions also come with a notion of complexity, which is called the conductor. So if you know anything about L functions, I mean, for example, think of the Riemann zeta function. They satisfy a functional equation which switches s and 1 minus s. And in there, some exponential factor appears. It's called the conductor. But if you don't know about that, just think of this conductor that I'll occasionally refer to as a measure of complexity. So if it's a big conductor, it's a very complicated L function. So here's the revisiting of the experimental strategy, and the same thing Johannes pointed out applies here. So we start with a finite set of L functions, and for each L, we consider an invariant of interest. So what that means is we start with the number field or an elliptic curve, we take its L function, and we also think of an invariant from that elliptic curve or number field, and we take the label data set. We have the training data set and the validation data set. We train the classifier on T, and we ask it to determine the invariance for V, and then we repeat this for different sets of T. So that's exactly the same slide, just with some more specifics for what we're actually going to do here. And here's some typical specifications, just on a very practical level. So often our experiments, we use vectors of length 100, which is a lot bigger than what we were doing with the polynomials. We take the label data set. It often actually has size around 1 million, but for some of the more complicated experiments, we have to drop down to 1,000 just because of available data. And the way we kind of make that choice is we bound the conductor. So we take L functions of a certain range in complexity. So we, for example, we might pick 0 to 1,000 for real quadratic fields, or even more than that. And then there's an ambiguity in T. You can take the training data set to be most of your sample size. You can take it to be not very much of it. So we typically try these three ranges, 0.2, 0.7, and 0.8. So that's the proportion of vectors that we use to train the classifier on. OK, so again, I'm starting the next section. So maybe if there's any further questions about that methodology, now's a good time for anyone to ask.
Sorry, should we already know what vectors you take? I mean, you have not talked about it. I mean, you just take the coefficients of the series, for instance?
Yes. Yeah, so I haven't told you what the L function is in any given case, but in every situation we study, there will be an L function, and I will tell you what it is for number fields, for elliptic curves, and so on, as we go through these case studies now.
But you don't start enriching it. You just take the coefficients for now.
Yeah, you just take the coefficients, and there is a kind of philosophical reason for doing that. So there's lots of famous formulas in number theory which relate the special values or the residue or the Taylor coefficients of an L function to all various different invariants. So somehow the invariants are in there formulaically, but we're going to try and get that from a sort of data science perspective, if just the distribution of the coefficients can give you the invariants. And I guess we'll come back to this in case study 3. So these random matrix models in case study 3, they are models for the coefficients. But what's kind of miraculous about that is they don't come from number theory. They're just some compact Lie group with a Haar measure. But we'll get to that. So right now what we're doing is we start with a number theory object, a number field elliptic curve. We attach its L function. Then we define a set of vectors which come from the coefficients, and we try and see if the machine can solve the problem. And the punchline is it can often quite regularly do that. And it's not really a surprise because of all these famous formulas, but I guess it's interesting that the machine is doing it and we're not just calculating. OK, so this first slide is about Dedekind zeta functions, and these are somehow the L functions attached to number fields. They're not actually denoted by L. A funny pedagogical thing is whenever you learn about L functions, the first example you see is the Riemann zeta function, which is not denoted by L. And more generally, this is true for Dedekind zeta functions. So it's a product over the prime ideals of 1 minus the norm of p to the minus s, the reciprocal of that, so to the power of minus 1. And if you multiply out that infinite product, you get the sum over the ideals in the ring of integers of the norm to the minus s. So if you took f equals q here, this is the Riemann zeta function. The first expression is its famous Euler product, and the second is the well-known Dirichlet series. So like I say, in the first expression, the p varies over the prime ideals, and in the second expression, I varies over the non-zero ideals. So we can group the terms to write this as a sum over the integers, which is the standard form for L functions I gave earlier. So if you do that, you get these coefficients an, and what that is it's the number of ideals of norm n. And the conductor is equal to the discriminant of the number field, if you know what that is. And another interpretation of it is it's the number that's divisible exactly by the primes ramified in F So it tells you where f is somehow a bit more complicated. Okay, so that's the Dedekind zeta function, and the important thing is this formula for an. It's the number of ideals of norm n. So here's a first experiment, and it's actually fairly promising. So we took the real quadratic fields with class number 1 or 2 and discriminant up to 1,000,000. I can't remember how many is in that set, but it's a lot. And then we considered the labeled data set, which takes the first m coefficients, and we do let m vary actually, but say m's 100, and maps it to the class number. And then randomly splitting this labeled data set into training and verification. Random forest classifier can predict the class number to very high accuracy, actually, about 0.96. And this confidence is a measure of how many false positives. So if that number is close to 1, it's a good sign. It has a technical definition that's not so important here. So actually, and there's something we can do beyond that. So already breaking the format of the methodology I gave you, we can have one range of discriminant for the training, and we can have another range of discriminant for the verification. So we can somehow extrapolate, and it's still able to perform quite well. So it is really seeing it picked up on some distribution in these coefficients that applies to higher ranges of discriminants. Possible kind of uses of that might be to extrapolate beyond current computational limits, although the problem is it's not always right. So, you shouldn't be relying on that for any serious purpose. But if you want to have a guess at what the class number is, then this might be a way to do it. So like you can see, the precision is usually quite high. It gets lower the bigger the discrepancy between the training range and the validation ranges, and the confidence gets lower as well. So that's a promising example, but somehow an even more elementary example goes much worse. So right at the start, I talked about the rank of the unit group of a number field. So if we consider cyclic extensions with bounded discriminant and degree 6, and let's consider the case where the rank is either 5, that's the totally real case, or 2, the totally imaginary case, and applying standard classifiers to the labeled data set, the first m coefficients go to the rank, gives actually very bad accuracy predictions, even though this is somehow a much more basic invariant. On the other hand, if you consider degree 4, 6, and 8 extensions, the same training data now labelled by the degree, the classifier is able to do that with high levels of accuracy. And that's kind of strange because, like I told you, the rank and the discriminant, the rank and the degree are both very simple formulas in terms of this invariant, the signature. So somehow machine learning is not able to detect this signature. So that's this final point here, that the degree is R1 plus 2R2, one simple formula, and the unit group ramp is R1 plus R2 minus 1 is another. So between these two experiments, you see somehow that machine learning isn't very good at detecting that signature. So actually, I'll go back to naive training because we found this a little bit frustrating at the time. So we wanted to just see if we could get it to work. And so here we're using defining polynomials. So now so every number field is defined by a polynomial. If it's degree n, it's a degree n irreducible polynomial. And we take the labeled data set, which is the n non-trivial coefficients. So from the constant term to the coefficient of x to the m to the rank. And trained on this data, random classifier can make much more accurate predictions. So in this case, the naive training is actually better. So what we've done is we've stratified it by Galois group and 2 signatures. And you can see that it's able to predict with precision and confidence above 0.9 again. And actually, another thing that does very well in this case is logistic regression. And the fun thing about that, it's very interpretable. So the next 2 slides is just me giving an explicit model for predicting the rank of a number field that's completely statistical, which is amusing, if nothing more than that. So we have this rounding function given a real number x. We let square brackets x denote the integer nearest to it. And we have this logistic sigmoid function, 1 over 1 plus the exponential of minus z. So the objective is for cyclic extensions of number field, for cyclic degree 6 number fields with rank 2 or 5 and bounded conductor, we aim to find coefficients for the coefficients such that 3 times the rounding of this logistic sigmoid function plus 2. So you can see that's a number in 2 or 5 because the logistic sigmoid function is either closer to 0 or 1. It can't be anything else. We want that to predict the rank. And you can actually find these coefficients very easily. So I think you just directly ask Mathematica to do it, and these are the numbers it gives. So with 94% precision, you can put these coefficients in, and then you have a statistical model for the rank of degree 6 number fields with extreme rank. I don't know why that would be useful, but it's quite fun to see it exists. And yeah, I guess that's one reason it's nice to do these defining polynomial calculations, because the number of coefficients is so small, you can really work this stuff out quite quickly and end up with very implicit models. So just to clarify, the accuracy of the model does vary with the rank and the discriminant, and it predicts rank 2 with accuracy greater than 0.9 for almost all ranges of the discriminant, with overall precision 0.99. And on the other hand, the model performs very poorly for rank 5 fields, with discriminants beneath a certain bound and above a certain bound. So that best fit really sort of optimizes in the middle of things. So that's just an explicit model, and it's the kind of thing you can do when you get high accuracy results. So it's just a fun example. So I'm moving on to the next section, hyperelliptic curves. Are there any questions about number fields at this point? Okay, that seems like a no. So I know at the start I was talking about elliptic curves, and a hyperelliptic curve is, it's got a similar Weierstrass equation. Let's not worry about it. The point is now the genus can be 2. So we'll do a couple of genus 2 things at the end. So here are the L functions attached to elliptic curves. So given a smooth projective geometrically connected curve of genus G and a good prime P, so that means the reduction mod P still has the same genus. This means the reduction is smooth. So that's called a good prime. We define this function Z, so again not denoted by L, x over fp with coefficient t, and it's the exponential of this point counting generating series. So the coefficient of t to the k over k is just the number of points over the finite field with p to the k elements, and it's the exponential of that. So that's called the local zeta function. And there were many famous conjectures about this. They're called the Weir conjectures. And one thing Weir himself proved is that in the case of curves over finite fields, this is a rational function, and it's got degree, the numerator is degree 2g in constant term 1, and as you can see, the denominator is this explicit thing. So these polynomials LP, they are the Euler factors of the elliptic L function. But I think what we're going to do next is we're simply going to write out what these Euler factors are, and then we're going to train on the non-trivial coefficient. So it's a slight break of format again from the original overview. So if E is an elliptic curve over Q and P is a good prime, then LP is 1 minus APT plus PT squared, where AP is P plus 1 minus the number of points over FP. And for a bad prime P, for the sake of concreteness, we just define AP by the same way, P plus 1 minus the number of points on E over FP. And for some integer I greater than 0, let Pi denote the ith prime. And for m positive integer, we introduce the vector AP1 up to APM in Z to the m. And the conductor QE is divisible only by the bad prime, so where there's ramification again. So this conductor is a measure of complexity. So it's slightly different to what we were doing before, because we're not taking all the Dirichlet coefficients. You could do that. You could multiply all these LP and calculate the Dirichlet series. We're just taking the non-trivial coefficients and the Euler factors. It's a similar concept. So again, we see that the machine is very good at distinguishing between rank 0 and rank 1, and we've even shown what happens if you start to vary m, and we've started to vary the training range of conductor and the discriminant range, the validation range of conductor. It's always above 0.99. It can get quite big. So yeah, this is the precision and confidence of a logistic regression classifier when asked to distinguish elliptic curves on Q with rank 0 from those of rank 1. Classifiers train the conductor range specified by the first column, using the number of Euler factors in the second column, and verified on the conductor range indicated by the third column. And the only, I don't expect you to look at all these numbers and make any sense of them, but the point is it does so quite accurately. So with that in mind, let's do some genus 2 stuff. So the zeta function is defined in exactly the same way. It's a rational function again, and it has the explicit denominator, and the numerator looks like this: 1 plus a1 pt plus a2 pt squared plus a1 p again pt cubed plus p squared t to the 4. So the point is these coefficients a, they are repeated, and actually if you normalize like p to the half t, I think it is, you get a palindromic polynomial. So there's some symmetry in this polynomial. So the two important coefficients are a1p and a2p. And for a bad prime p, we put them to be equal to 0 and p respectively. And now the training vectors, so we're breaking with the form a bit more extremely here, is something in z squared to the m, and it's all these pairs of non-trivial coefficients. And yes, so a bit of theory here. The Jacobian of a genus 2 curve is a two-dimensional abelian variety. The rational points are a finitely generated abelian group. So the second part of that was proved by Vey in 1929. And the whole reason we're doing this experiment is there's a new phenomenon, which is a significant proportion of the Jacobians have rank 2. So we can do a ternary classification now. And the supervised learning experiment, a logistic regression classifier trained on these Euler factors, is able to distinguish between curves of rank 0, 1 and 2 for conductors in the range up to 1 million, with precision around 0.97 and confidence around 0.96. So it really is able to do this in the elliptic curve case and the genus 2 case. Any questions about the curve experiments? Okay, that seems like a no. So the final section is random matrix training. So I can't remember why I mentioned it earlier, but random matrix models are very common in number theory because there's lots of questions about L functions. There's the Riemann hypothesis, there's a BST, and random matrices give statistical models of these things. And since we're doing machine learning, it's a kind of statistical computational tool, it makes sense to investigate this interplay.
Just one more, Tom, there's a question. I think Ahmed put his hand up.
Hi, I'm just wondering about the statement that the significant proportion of genus 2 curves is 2. I don't believe that that's the case. I know that there are lots of products.
Yeah. So I didn't make a rigorous mathematical statement there. What I really meant was on the database I'm using up to conductor 1 million, there is enough of them to try and machine learn that.
Okay.
So I didn't mean to make a rigorous asymptotic statement. I didn't mean to imply anything too extreme. I just meant that practically speaking, we can include that. But if you try it with elliptic curves, there's so few examples of 2 that it basically never predicts it.
Okay, thank you.
Okay. Thank you for the question. So in this final thing, we're going to talk really about endomorphism types. And the reason for that is a complicated conjecture called the Sato-Tate conjecture. And I didn't really want to, I'm not enough of an expert to give a full-on exposition to this, so I'll leave it a bit hazy. But a generic elliptic curve over Q has endomorphism ring isomorphic to Z. And the Sato-Tate conjecture, which is actually a very recent theorem for elliptic curves over totally real fields, implies that the Euler factors are distributed the same way for all generic curves, ones with that endomorphism ring isomorphic to Z. And more precisely, they're distributed like the characteristic polynomials of random matrices in SU2. So I mentioned earlier, if you actually calculate what the characteristic polynomial of a random matrix in SU2, you'll get something that looks quite a lot like the Euler factor. So the non-generic cases are those with CM. In this case, the Euler factors are associated with Hecke characters, and they're distributed differently. So one way to see this immediately is that Hecke character is 0 a lot more often than a generic coefficient of an elliptic curve. So even just by looking at the number of zeros, you can quickly see that these two L functions have coefficients distributed differently. And to be more precise, the distribution matches random matrices in the normalizer of U1 and SU2. So it's not really a surprise given what I've just told you about counting zeros, but a naive Bayes classifier trained on random matrices and validated an elliptic curve. So now our training data set and our validation data set are really quite distinct from each other, is able to distinguish CM between CM and non-CM. And here's an image which shows you how the precision and confidence varies as you increase the number of coefficients. So it doesn't take very long for it to be quite high. So I think already it's close to 100% precision here, and this looks like something less than 100. You can do this by purely arithmetic means. It's not completely surprising, but I guess it's nice to see the machine learning methodology. And some of them weirdly, some of the machine learning methodology doesn't perform at all that well in this basic task. So the naive Bayes classifier works very well. And I think the key that one makes is it treats all variables as independent. And that's kind of a standard assumption in number theory, that the behavior at different primes are independent. So generic genus 2 curves, and a little hint of what to come here. I've mentioned that this is actually supervised learning. Later on we'll see one unsupervised experiment, the only one. According to the generalized Sato-Tate conjecture, Euler factors of generic genus 2 curves are distributed like random matrices in USP4. So again, if you calculate the characteristic polynomial, you get a palindromic thing, which looks again like the Euler factor of a genus 2 curve. And a naive Bayes classifier trained on random matrices can again separate generic and non-generic. But this time, unlike with elliptic curves, there's a lot, actually, 54 and 33 over Q of non-generic cases, all distributed differently, corresponding to different endomorphism types of the curve. Oh, it took a second to load then. Here's an unsupervised experiment, actually. So without telling the classifier, so unsupervised means we don't tell the computer the labels. So computer is able to distinguish these two cases, generic and non-generic. They're the two big blobs. And what these blobs are is we took a 400-dimensional image of all the coefficients and we asked it to the computer, it's called the principal component analysis, to project into 2 dimensions in such a way that it separates these two cases. So this is just the computer picking up on some clustering or some other biases in the distribution. And this is the one and only unsupervised experiment in this talk. And actually unsupervised learning is able to distinguish all the non-generic cases, but since I haven't told you what these are, I won't get into that. But what I will quickly say is that naive Bayes is also able to distinguish these non-generic cases. So there's 33 of them, and here's a particular 5. So this is a particular endomorphism type. So again, you train on random matrices and validate on curve data. And again, you can see that quite quickly it becomes very accurate. So there is a theorem, I think it's of Sutherland and a student, saying that you can actually predict the Sato-Tate group or the endomorphism type from, I think they even go down to a single Dirichlet coefficient, but they don't tell you which one. And machine learning kind of indicates it's possible to do from not many. It's not quite one, but at least you know which ones you do in the first 20 or something. And again, none of this is a particular surprise because it's very clear the numbers are distributed differently. The only point is that machine learning is doing it rather than us humans doing it. So finally, some adverts, just a few preprints on the archive. And also, if you want to see more talks about machine learning in pure maths, there's several linked to this website at the bottom. And that's the end of my talk.